Hello, welcome back to the online course on analog integrated circuits. In this lecture, we are going to discuss analog multipliers. Analog multiplier is a circuit which produces output voltage proportional to the product of the two analog input signals. Here is the question which is asked in previous year examination. Discuss the different method for implementing analog multipliers. Also, we can expect a question from another topic which is Gilbert cell. Let's start with the basics of analog multiplier. This is the typical representation of analog multiplier. As I said earlier, analog multiplier is the circuit which produces the output proportional to or equal to the product of two analog input signals. So we can write the output of the analog multiplier, which is V0 is equal to sum K into Vx into Vy, where K is the scaling factor or proportionating factor which depends on the system. Depending on the possible polarity of the input signals, analog multiplier is classified into single quadrant multiplier where they only accept single polarity for both input signals or input signals are unipolar, and therefore output is also unipolar. Two quadrant multipliers are those where one of the input signal has to be unipolar but the other one can be bipolar, and the output is therefore bipolar. And the four quadrant multipliers are those in which both input signals can be bipolar signals and the output is also a bipolar signal. So this will be the most flexible type of analog multiplier. Analog multipliers can be implemented both as discrete circuits or as a single integrated circuits. There are many methods available for implementing analog multipliers like log-anti-log type multiplier, transconductance type multiplier, pulse width and amplitude type of multiplier, etc. In this transconductance type multiplier, Gilbert cell analog multiplier is the most popular analog multiplier and it is the basis for the most of the multiplier system. Let's look at the different methods for implementing analog multiplier. First one is log and anti-log multiplier. Here, this is the basic mathematical principle behind this method. First take the logarithm of both input, then add those values, then we will get log Vx plus log Vy. We know that log A plus log B is equal to log AB. Hence, it comes log Vx into Vy. Taking anti-log of this will produce the output which is equal to Vx into Vy. We have already studied how a log amplifier and anti-log amplifier can be implemented using operational amplifier. This method is limited to positive polarity signals, so it belongs to single quadrant analog multiplier. Another method is transconductance based analog multiplier, which uses the transconductance property of the transistor. Let's look at one of the method that depends on the exponential transfer function of bipolar transistors. It is emitter coupled pair as a simple multiplier. In this method, emitter coupled pair is used as the basic element. Let us discuss what is emitter coupled transistor pair. Here is a circuit in which two transistors are coupled through emitter and connected to a constant current source. Input voltage VID is applied in between the base of transistors. Positive of the input is connected to the base of Q1 and negative is connected to the base of Q2. And IC1 is the collector current of Q1 and IC2 is the collector current of Q2. The output is taken between the collectors of Q1 and Q2. So the output voltage is proportional to the difference between the collector currents. For an emitter coupled pair, the current IEE and the collector current are related as IC1 is equal to IEE divided by 1 plus e raised to minus VID divided by VT, and IC2 is equal to IEE divided by 1 plus e raised to VID divided by VT. Here you just note down a relation between the input and the collector current. While considering the collector current of Q1, that is IC1, the base is connected to the positive of the input, and this term here it is negative VID divided by VT. And in the case of Q2, negative of the input is connected to the base of this transistor, and here we have e raised to positive VID divided by VT. Now let's calculate the change in collector current. The change in collector current delta IC is equal to IC1 minus IC2. We have IC1 is equal to IEE divided by 1 plus e raised to minus VID divided by VT, and IC2 is equal to IEE divided by 1 plus e raised to VID divided by VT. Apply these IC1 and IC2 in the change in collector current equation, then delta IC is equal to IEE divided by 1 plus e raised to minus VID divided by VT minus IEE divided by 1 plus e raised to VID divided by VT. Here we have IEE is common, so we can write it as delta IC is equal to IEE into 1 by 1 plus e raised to minus VID divided by VT minus 1 by 1 plus e raised to VID divided by VT. Then take the term e raised to minus VID divided by 2VT outside from this denominator term and e raised to VID divided by 2VT from this term, then the equation becomes delta IC is equal to IEE into 1 by e raised to minus VID divided by 2VT into e raised to VID divided by 2VT plus e raised to minus VID divided by 2VT minus 1 by e raised to VID divided by 2VT into e raised to minus VID divided by 2VT plus e raised to VID divided by 2VT. Now let's subtract these terms, then the equation becomes delta IC is equal to IEE into e raised to VID divided by 2VT into e raised to minus VID divided by 2VT plus e raised to VID divided by 2VT minus e raised to minus VID divided by 2VT into e raised to VID divided by 2VT plus e raised to minus VID divided by 2VT. whole divided by e raised to minus vid divided by 2vt into e raised to vid divided by 2vt plus e raised to minus vid divided by 2vt into e raised to vid divided by 2vt into e raised to minus vid divided by 2vt plus e raised to vid divided by 2vt. Now these terms are reciprocal to each other, then these terms will get cancelled and these terms are same, so we can take this term as common, then the equation become delta IC is equal to IEE into e raised to minus VID divided by 2VT plus e raised to VID divided by 2VT into e raised to VID divided by 2VT minus e raised to minus VID divided by 2VT whole divided by e raised to vid divided by 2vt plus e raised to minus vid divided by 2vt into e raised to minus vid divided by 2vt plus e raised to vid divided by 2vt. Now these terms will get cancelled. Therefore, delta IC will be equal to IE into e raised to vid divided by 2vt minus e raised to minus vid divided by 2vt whole divided by e raised to vid divided by 2vt plus e raised to minus vid divided by 2vt. This term is the expression for tan hyperbolic function, that is tan h of x is equal to e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. Then the equation can be written as delta IC is equal to IEE into tan h of VID divided by 2VT. If VID divided by VT is very much less than 1 or VID is very much less than VT, then tan h of VID divided by 2VT will be almost equal to VID divided by 2VT. Look at the DC transfer characteristics of emitter coupled pair. Here the function is almost linear near to the origin. That is when the value VID is very less than VT. Then delta IC is almost equal to IEE into VID divided by 2VT. If we use current mirror instead of that current source IEE and make the current is proportional to the another input VI2, look at the circuit. Here IEE is almost equal to K0 into VI2 minus VBE on. Apply this current in change in collector current equation, then delta IC is equal to VID into K0 into VI2 minus VBE on divided by 2VT. Here the output voltage depending on the change in collector current, hence we can say that Vout is directly proportional to the VID into VI2 minus VBE on. If VI2 is very much greater than VBE on, so we can ignore this VBE on, then we can say that V0 is directly proportional to the product of VID and VI2. Here VI2 should be higher than VBE on and VID should be small. VI2 should be greater than VBE on means that multiplier functions only in one quadrant. So this type of multiplier is belong to two-quadrant multiplier. Let me stop here today. We will continue in the next class with a modified version of this circuit, that is Gilbert multiplier cell. Okay, thank you.